In class, we've already practiced using our calculator using sequence, series, and sigma notation. But in this assignment, we're going to start even simpler than that. If you're only calculating a few rectangles, you might just decide to add them individually. So let's first look at our example here of our graph f of x equals x cubed. And if we were using a square graph, we know that this graph would rise very quickly. So you'll notice in the graph I've already drawn for question 1a that I do not have a square grid. I have rectangular units, so my x units are much wider than the y units, so that we can easily see what we need to do for L3 is we need to divide this into 3 different units. Well, if our integral goes from 0 to 3, then clearly our delta x value is pretty simple to compute. Remember, we have a formula for delta x, that it's the width of the interval divided by the number of rectangles. But we need not make that complicated here. Of course, if we're dividing 0 to 3 into 3 rectangles. So if we are doing left-hand rectangles, then notice what we want to do is choose the height at the left-hand side. So our first rectangle is actually a segment. That sometimes is too simple and it confuses us. So we're taking the heights of the rectangles on the left-hand side. And let's compare that right away to part B, where we're going to be doing the same problem, the area from 0 to 3, but in this case, we are going to be using right-hand rectangles. So this time we would measure our rectangles to have a height at the right-hand edge. So we can see that our first rectangles are too small and our second rectangles are too big. They go above the curve. But the height of each rectangle is simply a y-coordinate. So let's take this point, for example, and analyze it. That point would be at 2, f of 2. So our y-coordinate comes from plugging in the x-coordinate, the x sub i's, as we're going to call them. All right, so let's quickly do this computation here. So we are approximating the integral. The integral would be the exact area under the curve. So we are approximating the integral from 0 to 3 by using 3 left-hand rectangles, and that would be the height of each rectangle times the base of each rectangle. The base is always equal. Our delta x is our base, so if it's equal, we might as well factor it out in front. And here the heights of our rectangles, if we let, and I should be very careful to write this down, if I let f of x be equal to, sorry, that's our next problem, x cubed is this problem. Let f of x be equal to x cubed. And in your calculator, of course, you're going to make that y1. All right, so our first rectangle has a height of f of 0. And our second rectangle has a height at 1. And our third rectangle has a height at 2. Wow, I'm having trouble writing here. All right, so we don't need a calculator for this problem. We can cube these small numbers, 0 cubed, 1 cubed, and 2 cubed. So we come up with an area of 9 as the approximate value for the integral. So now let's repeat the same. We're approximating the area, but this time we're using R3. So this time we want to measure the heights on the right-hand side. So our first rectangle had a height at f of 1, and our second rectangle had a height at f of 2. And our third rectangle has its height at f of 3. So it's really where you start and where you finish. You'll see that is the only difference between these. So f of 1 is our 1 cubed. F of 2 is 2 cubed, which is 8. And f of 3 is 3 cubed, which is 27. So I think we can add this up and come up with an area of 36. And we know that clearly, visualizing it, that's clearly an overestimate. So what's our next option? Our next option is to do 3 rectangles, but this time let's measure their heights right in the middle of the interval. So instead of using the left or the right hand edge, let me switch colors here and let's pick our heights to be right in the middle. So here we would measure this rectangle to have its height would be f at 1/2. And our next midpoint would be at 3/2. So this rectangle is going to have its height here will be f of 3/2. And then we're going to measure our last rectangle right in the middle of the interval. So let's use 5/2. So now we're going to be adding up these shaded regions. And it might not be a perfect answer. Definitely will not be a perfect answer, but you might say, well, it's a better estimate than either of our other 2 answers. So now to approximate the integral from 0 to 3, we are approximating using 3 midpoint rectangles. Now be careful here, our delta x is still the same. Our delta x for each of these rectangles is still 1. So the base of each rectangle is still 1. The only thing that's changing is where are we measuring the heights. So, and you can grab your calculator if you don't want to do this arithmetic, but I think these numbers are still small enough that we can cube them. 1 cubed, or 1/2 cubed is 1/8. 3/2 cubed is 27/8, and 5/2 cubed is 1/25. So since they have a common denominator, I think we could add those together. And it looks like, what, 153/8? So what do we think about overestimates and underestimates? Well, let me scroll back so you can see again. Remember, the graph was increasing, appears to be the difference. When the graph is increasing, the left-hand rectangles were below the curve. The right-hand rectangles were above the curve. So L3 is an underestimate. R3 is an overestimate. And M3, I think we would have to say it's a bit unclear. You could take a look and see what you think if you compare this region that you didn't count with this region that you did include. So you could guess whether it's an overestimate or an underestimate, but that might depend very much from one graph to another. And why do we think that's true? Is it true because the graph is increasing? Is it true because the graph is increasing? So this might take some investigating for us. But that might be my first hypothesis here, that it doesn't have to do with concavity. Does it have to do with increasing, decreasing? All right, and then we're going to do a little question here, preview of something we'll prove as a theorem. So learning how to use the integral key on your calculator. It's in the calc menu, but it's also above the 7 key, so you can use a shift key for integral. And it has 4 arguments: the expression that you want to integrate, the independent variable, the with respect to, and then it has the lower limit and the upper limit. So the one we were just doing went from 0 to 3. So let's find out what your calculator gives us as a better estimate of this area. So try plugging that into your calculator, see what you come up with. And I came up with 81/4, or if you did the decimal form, I guess 20.25. All right, what's the simplest antiderivative of this function? Well, remember how we do an antiderivative? We raise the exponent, and then this one would have a coefficient of 1, so we would divide that coefficient by our exponent of 4. All right, so an antiderivative, remember we would have to add a constant here, but it says what's the simplest value. So if we let c be equal to 0, so this is not all antiderivatives, this is just the simplest antiderivative. And you'll see in the next few days why we're doing this. All right, let's call this capital F of x. The antiderivative of small letter f, we often use capital letter F. And let's see what happens. What if we put 3 into that function? So our antiderivative at 3 to the 4th power is 81 over 4. And f of 0 is, of course, 1/4 of 0. And we come up with 81 over 4, and the point here was, do you notice that it might not be coincidence that these two values turned out to be the same result? So a preview of a theorem we'll be studying. All right, back to practicing some more Riemann rectangles, and again, we're only doing 3 rectangles here. So you can use your sigma and sequences on your calculator, or you can just draw the 3 rectangles and see what you come up with here. All right, so if we divide this into 3 rectangles, 1/3 of pi over 2 is pi over 6. So remember again, our delta x formula is b minus a over n. So here we're going from pi over 2 to 0, dividing that 3 ways. So of course that formula isn't meant to be something you have to show on paper. Our delta x value, the distance between these, I think you could easily see was going to be pi over 6. And then we go another pi over 6, so we can either call this 2/6 pi, or of course that's pi over 3. And then we could call this 3/6 pi, but of course that's pi over 2. So first we're going to use our left-hand rectangles, and now you can see something very different happens. This graph is decreasing. So now look what happens. The left-hand rectangles appear to be the overestimate. So for our integral from 0 to pi over 2 of cosine of x, we're going to estimate this using L3. And L3 would be 3 of these rectangles. You could do base times height separately. Or since the base is always pi over 6, you could factor that out in front. Your delta x is your base. And then if we let f of x be equal to cosine x, then we would have f of 0 plus f of pi over 6 plus f of 2/6 pi, which is pi over 3. And you could use your calculator, or because we know cosine of these special values, cosine of 0 is 1, cosine of pi over 6 is square root of 3 over 2, cosine of pi over 3 is 1/2. So if we think of this as 2 over 2, so we have a common denominator, pi over 6 times 3 plus square root of 3 over 2. So we could write it as pi over 12 times 3 plus square root of 3. And let me grab my calculator here. It would be perfectly fine if you left this exact answer, or if you had done this with your calculator and green diamond enter. I think I have 1.239. So either of those values. All right, let's repeat the process, but this time we're going to use right-hand rectangles. So you can see that our right-hand rectangles will be too small, and this third one will in fact have a height of 0. So we're still at pi over 6 and 2/6 pi, or pi over 3. So our delta x value hasn't changed. Our delta x value is still pi over 6. So we're approximating the integral from 0 to pi over 2. To find that, we're using 3 rectangles as our approximation. And our base of each rectangle, and this time the heights we're measuring at the right-hand edge. So our first rectangle would have a height of f of pi over 6, and our second would be f of 2/6 pi, or pi over 3, and our third has a height of f of 3/6 pi, or of course pi over 2. And again, we know these values from our special triangles. Cosine of pi over 6, cosine of pi over 3, and cosine of pi over 2 is 0. So here we would have, oops, what did I just do here? That should say 1/2. So we've got a common denominator already. So square root of 3 plus 1, or turn it around the other way, I guess. Pi over 12 times 1 plus square root of 3 would be our exact answer. Or if you were using a calculator, I think 0.715. All right, so we can see that these rectangles were too low. They had a lot of area that they didn't cover. So this time, things seem to be reversed. So this time L3 is an overestimate. And R3 appears to be an underestimate. And do we know why? Well, I think my theory is it because f of x is decreasing. So again, we haven't done anything to prove that yet, but that certainly by visual observation appears to be the case. All right, let's see what happens here if we use our integral. Remember, look above the 7 key or in the calc menu, and then put in these 3 arguments. So pause, try that with your calculator. And it comes up with an exact value of 1. So let's find out if the same trick might work. An antiderivative of cosine. So we're reversing our thinking and we're saying cosine is the derivative of what? Cosine is the derivative of sine. And of course we could add a constant, but here we're looking for the simplest value, so let's let c equal 0. So it's not that that constant wouldn't still appear, but let's just let it be equal to 0. And now let's test out what happens if we use the upper limit and the lower limit of our integral. So the sine at pi over 2 is 1, and the sine at 0 is 0. So that should be a minus sign. And sure enough, twice now, it appears to work that we got the same result. So we're going to have to investigate whether that will always be true and why is it true. Okay, here's a problem that will definitely appear on every quiz or test that you'll take. What can we do if our velocity data is only given in tabular form? So we have a table of discrete points. We don't know what happens in between these values. So the area under the velocity curve gives us distance. We've already come up with that idea. But here we don't have an algebraic formula, so the best we can do is approximate using these rectangles. So these Riemann rectangles are pretty important. So L5, we would use the left-hand rectangle. So we would start our first interval, would go from 0 to 4. So it would have a delta x value of, 0 to 4 is 4 as its width or its base. So the base of each rectangle is the delta x value, and the height would be the velocity on the left-hand side. And then our next rectangle would go from 4 to 6. So it would have a base or a width of 2, and its height would come from the left-hand side, which would be v of 4. All right, now maybe I can make this even easier if I do the next step at the same time. The velocity at 0 was 17. So the width times the height, and then the width of 2 times v of 4, the height is 21. So notice that we're taking our heights on the left-hand edge of each rectangle. So our next rectangle goes from 6 to 9. And we would measure its height as the velocity on the 24, getting ahead of myself, velocity of 6, which is 24. And then our next rectangle goes from 9 to 14, so the delta x is 5, and we're going to take v of 9 as the height. And our last rectangle from 14 to 16 has a delta x of 2, and we're going to take the velocity on the left-hand side. Oops, I keep getting one step ahead here, which would be the velocity at 14. And the velocity at 14 is 31. So you can grab your calculator, no need to do that arithmetic by hand. And you can verify whether I've punched that in my calculator correctly. I came up with 389. All right, now let's repeat the same table, but now we're going to use 5 right-hand rectangles. So the concept is the same. However, we're going to measure the heights on the right-hand side. So remember that in the first rectangle, the base is still going to be 4, but this time we're going to measure the height on the right-hand edge. So we're going to set this up as a delta x, but then our height here we're going to measure with the right-hand y-coordinate. So this will be 4 times 21. So we're going to get a different answer. Same idea of using rectangles. The next interval, the delta x was 2, but this time we're going to use the velocity at the 6 at the right-hand side. So that's going to be 24. And our next rectangle still has a delta x of 3, just like it did up above, but this time we're measuring the velocity on the other side. So this will be a 29. And our next rectangle has a distance or a base of 5, and we're going to measure the velocity at 14. So you'll notice again that it's the start and the end that differ. So our delta x's stay the same, but this time we're measuring the velocities on the right-hand edge of the rectangle. So this would be a 28. And then you can pause here if you haven't done this already. And with the calculator, I come up with 430. All right, so do we know which of these is actually the better answer? Of course not. We don't have a good picture of this graph. And again, with discrete data, we really have no clue what happened to the velocity between 9 and 14, for example. So can we make any predictions about which is the best? So can make no predictions because we don't have a visual picture of the function. We don't have an algebraic formula. We don't have a graphing view of this. So these are estimates of the distance only. But remember that total distance was the area under the velocity curve.